For the longest time, the path to solving bigger scientific problems seemed pretty straightforward. Just build a bigger computer. But what if there's a different way, a smarter way, one that doesn't rely on billions of dollars in hardware, but on the sheer elegance of a really well-designed algorithm? So in this explainer, we're going to dig into this question. Can clever code actually replace raw computing power?
I mean, this is the big one, right? At the very heart of modern science is this massive question. If you want to design new drugs or invent new materials or just understand how the universe works, you need to be able to create digital copies of reality. But simulating every single interaction, every particle, every force, well, that's a task so huge it's basically infinite. So where do you even start?
For a long time, the answer was always that column on the left. Just throw more hardware at it. It's a brute force approach that's not only incredibly expensive, but it also eventually hits a hard physical wall of what we can even build. But that column on the right, that suggests a totally different path, one based on elegant, cost-effective solutions that tap into our own creativity. This is the real battle here, brains versus brawn, but in digital form. And we get a refreshingly direct answer right up front. Can smarter code make a difference? The answer is a resounding yes. The huge gains, the real breakthroughs, they come from this powerful combo: clever algorithms, efficient data structures, and maybe the most important part, approximations that are actually aware of the underlying physics. It's not magic, it's just really, really smart science.
Okay, so how do we actually put this into practice? Well, it all starts with one single fundamental principle. Before you write a line of code, before you simulate even one atom, you have to know exactly what you're looking for. And that brings us to two really crucial terms. First, the observable. That's the one specific thing you actually care about, like a material's elasticity or its energy. And second, the error budget. Basically, how much inaccuracy can you live with? Is 5% okay? 1%? Nailing this down is everything, because it tells you exactly where you can afford to cut corners. I love this analogy because it makes the whole idea so clear. When you bake a cake, your observable is a tasty cake, right? You have to measure the flour precisely because that's critical. But you don't need to track the exact position of every single molecule inside the egg. I mean, that would be completely insane, and it wouldn't make the cake taste any better. Scientific simulation is the exact same way. You focus your energy on what actually matters for the final result. Okay, so we've got our guiding principle. Now let's open up the toolkit. We're going to look at three major strategies. Think of them as the secret weapons scientists use to make their simulations way faster and smarter, all without having to buy a new supercomputer.
So, strategy number one is all about focus. Instead of treating the entire simulated world with the exact same super high level of detail, you zoom in. You spend your precious computational budget only on the parts that are the most critical to what you're trying to measure.
And this zooming works in a few really clever ways. With multi-scale modeling, you could simulate the absolute core of a chemical reaction using hyper-accurate quantum mechanics, but then model all the less important stuff around it with a much cheaper, simpler method. Or with adaptive resolution, the simulation itself actually decides where to focus, cranking up the detail on the fly only where the action is happening. See? It's all about avoiding work you don't actually need to do.
All right, our second strategy feels like it's straight out of Hollywood. What if, instead of running an incredibly expensive A-list calculation every single time, you could train a cheaper, faster stunt double to do most of the work for you? Well, that's pretty much exactly what scientists are now doing with machine learning.
So here's the game plan. You do a few very expensive, super high accuracy simulations, then you feed all that precious data to a machine learning model and train it to predict the outcomes. This ML model, it basically becomes your digital stunt double. It can run millions of scenarios for a tiny fraction of the cost and with almost the same accuracy. And with cool tricks like active learning, the model is even smart enough to know when it's confused and needs to call in the A-list actor for a new, tricky scene. Now, this last strategy is less about the fancy math and more about, well, logistics. See, it's not just what you calculate, it's how you organize your data. You can have the most brilliant algorithm in the world, but if it spends all its time just searching for the information it needs, the whole thing just grinds to a halt. Think of it like organizing a library, right? Instead of just throwing all the books into one giant pile, you organize them by subject. These clever data structures do the same thing for simulations. For example, instead of making the computer check every single particle against every other particle, something called a cell list groups them by location, so it only has to check its immediate neighbors. This kind of smart filing system leads to absolutely massive speedups.
So we have our guiding principle, and we have our toolkit of strategies. But how do all these pieces actually fit together on a real project? Well, it turns out there's a pretty practical step-by-step roadmap for making it all happen. This 6-step process really shows the logic. Step 1, you define your target. Then, you build a small, perfect reference model, just so you can train your machine learning stunt double. Once that's trained, you plug that fast model into your bigger simulation, and you optimize the whole thing with smart data structures. And finally, and this is so critical, you validate everything against the real world, and you iterate, making sure your smart shortcuts are still giving you answers you can trust. Look, following this roadmap takes a lot of expertise and some really careful planning. So, what's the reward for all this brain power? Well, the payoff is absolutely staggering. But like with everything in science, there is, of course, a catch. No, that is not a typo. By combining all these techniques, the computational cost for a lot of problems can be slashed by a factor of 1,000,000. That's the difference between a simulation taking 100 years and taking about an hour. It completely changes the kinds of questions we can even dare to ask. But here it is. Here's the catch. This unbelievable speedup comes from one fundamental trade-off. You are making a conscious choice to sacrifice perfect, 100% accuracy in exchange for feasibility. You're trading the dream of a perfect simulation, which would be infinitely slow and expensive, for the reality of getting a useful answer quickly and affordably. It's a shift from pure exactness to controlled approximation. And we have to be really clear about the other limits. This is not a silver bullet. For certain really complex quantum problems, these compression tricks just don't work. And because you're using approximations, error control and constant checkups aren't just a good idea. They are absolutely essential to make sure you can trust your results. The bottom line is, some problems are just fundamentally hard, and no algorithm we have today can magically get us around that. So at the end of the day, this is about way more than just saving money on hardware. It's really a shift in how we approach problem solving itself. It proves that a better idea can be exponentially more powerful than just a bigger machine. And that leaves us with a really fascinating final thought. What challenges that seem impossible today will become solvable tomorrow, not because we built a faster computer, but because someone, somewhere, came up with a smarter way to ask the question.